Fine. Let's start. The observable universe is 93 billion light-years across. It contains roughly 2 trillion galaxies, and almost every cosmologist alive will quietly admit that it is probably not everything. The question isn't really whether something exists beyond what we can see. The question is what, and it turns out scientists have real answers to that. Some of them are beautiful, some of them are genuinely terrifying, and a few of them make the question itself fall apart. Here are 10 of the most realistic theories about what lies beyond the edge of everything we can observe. Number 10. The axis of evil. That name is not a metaphor. That is the actual name physicists gave it. In 2003, NASA's WMAP satellite produced the most detailed map ever made of the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in existence, a snapshot of the universe when it was only 380,000 years old. Scientists expected it to look essentially random, uniform, isotropic, the same in every direction, the way the universe is supposed to be. It wasn't. The 2 largest temperature patterns in that map, the quadrupole and the octopole, which represent the biggest structures we can see imprinted in the ancient light, were aligned with each other. That alone would be strange. But they were also aligned with the plane of our solar system, with the path the Earth traces around the Sun, with us. The cosmological principle, one of the foundational assumptions of modern physics, says that the universe has no preferred direction, no axis, no orientation. The universe should look essentially the same from anywhere, pointing anywhere. What WMAP found suggested otherwise. Physicists assumed it was an instrument error, a contamination from our own galaxy's dust, a statistical fluke. They moved on and waited for better data. Then, in 2013, the Planck satellite released its results. Planck had better resolution, different instruments, and a completely independent methodology. It confirmed the alignment. Dominic Schwartz at the University of Bielefeld said it plainly. For a long time, part of the community was hoping this would go away. It hasn't. The axis points roughly in the direction of the Virgo constellation. Nobody knows why. A 2016 analysis found no decisive evidence for anisotropy. Others insist the signal is real. The debate hasn't resolved. But here's the thing that sits with you after a while. If the universe does have a preferred direction, if space itself is oriented, then something set that orientation. And the most natural explanation is that whatever set, it exists beyond what we can see. The universe may not be indifferent to direction. It may have one, and we just happen to live along it. Number 9. The soccer ball universe. In October of 2003, same year as the WMAP results actually, a team of cosmologists led by Jean-Pierre Luminet of the Paris Observatory published a paper in Nature with a genuinely strange proposal. The universe, they argued, is finite. It has a specific shape, and that shape is a 12-sided soccer ball. More precisely, they proposed the universe has the topology of what's called a Poincare dodecahedral space, a closed, positively curved geometry with 12 pentagonal faces, where opposite faces are connected, with a 36-degree twist. If you fly out through one face, you re-enter through the opposite face, rotated slightly. The universe loops back on itself. No edge, no boundary. Just wrap. The volume of this universe, if the model is correct, would be about 80% of what we can currently observe, meaning the universe would actually be smaller than our observable bubble. This sounds like science fiction, but it was published in Nature, one of the most rigorous scientific journals on Earth, and it was offered as a specific explanation for an anomaly in the WMAP data. The fact that the largest scale fluctuations in the cosmic microwave background were weaker than the standard model predicted. A finite wrapping universe would suppress those fluctuations. The math worked. If this is correct, the answer to what's beyond the observable universe is you, us. Everything we can already see, wrapped around, and coming back from the other direction. You'd see ghost images of our own galaxy, billions of years younger, distributed across the sky like a hall of mirrors that curves back on itself. The Planck satellite's 2015 data didn't find the matched circle patterns in the sky that this model would require, which either rules it out or means the topology exists at scales just too large to detect. But there's something quietly destabilizing about it. The entire premise of this video, 10 theories about what's beyond the universe, briefly has no answer. Because in this model, beyond is just back. The question eats itself. Number 8. Dark flow. September of 2008. Alexander Kashlinsky, an astrophysicist at NASA's Goddard Space Flight Center, publishes a paper that his own team describes with the words, "We never expected to find anything like this." What they found was this: galaxy clusters, not individual galaxies, but enormous gravitationally bound collections of hundreds or thousands of galaxies, were moving. Not just expanding with the universe, the way everything is. Moving, streaming, all flowing in the same direction toward a specific region of sky between the constellations Centaurus and Vela at roughly 2 million miles per hour. Galaxy clusters spanning up to 6 billion light-years from Earth, all moving the same way. Kashlinsky's team used the WMAP satellite and a technique called the kinematic Sunyaev-Zeldovich effect, the way hot gas inside galaxy clusters leaves a faint imprint on the cosmic microwave background, to measure the velocities of over 700 clusters. The motion was consistent, it was coherent, and it could not be explained by any known concentration of mass within the observable universe. Kashlinsky called it dark flow, and he suggested it was being caused by gravitational attraction from structures beyond the cosmic horizon. Matter we cannot see, pulling on matter we can. NASA's own press release noted that some scientists were raising the possibility of it being caused by a sibling universe, or a region of spacetime fundamentally different from our own. That wasn't a fringe website. That was NASA. But here's the thing. In 2013, the Planck satellites team reanalyzed the data and found no statistically significant dark flow signal. Kashlinsky disputed the methodology. He argued Planck wasn't using the right technique. He kept publishing. The signal, in his data, never disappeared. The debate has never fully resolved. No consensus has been reached. And somewhere out there, either Kashlinsky is measuring a real gravitational tug from beyond everything we can see, or 700 galaxy clusters are all doing the same thing for no reason. Neither option is particularly comfortable. Number 7. The Big Rip. February 2003. Robert Caldwell at Dartmouth College, along with colleagues Mark Kamienkowski and Nevin Weinberg, publish a paper in Physical Review Letters. The title is Phantom Energy and Cosmic Doomsday. You can tell from the title that this is going to go well. The setup: dark energy, the mysterious force accelerating the expansion of the universe, has a parameter called its equation of state, basically a number describing how it behaves as the universe expands. The standard model assumes this number is -1, a cosmological constant. Dark energy stays the same as the universe grows. But what if it's slightly less than -1? What if it's -1.1 or -1.2? What if dark energy gets stronger as the universe expands? Caldwell's paper showed what happens, and it's precise, uncomfortably precise. If dark energy is phantom energy, if that number dips below -1, then the expansion of the universe doesn't just continue. It accelerates, and accelerates, and keeps accelerating without limit until it reaches infinity in a finite amount of time. Everything gets ripped apart. First, structures too spread out to hold themselves together. Galaxy clusters, gone. Then, after more time, galaxies themselves. Then solar systems. Then planets. Then, and this is the part that makes you put down whatever you're holding, atoms. The electromagnetic force holding electrons to nuclei isn't strong enough. Everything dissolves. Caldwell's paper gives you the timeline. About 60 million years before the end, the Milky Way is torn apart. About 2 months before the end, our solar system disintegrates. About 30 minutes before the end, Earth is shredded. In the final fraction of a second, atoms themselves come apart. And then, space-time tears. Just stops. Current observations put dark energy's equation of state very close to -1, but the error bars are still wide enough that phantom energy remains physically possible. We do not know which side of that line we're on. Here's the part that stays with you. Beyond our current cosmic horizon, the universe has already expanded further than we can see. If phantom energy is real, those regions are already further along the RIP timeline than we are. The unraveling, if it's happening, started somewhere we cannot observe, and it is moving toward us at the speed of light. Number 6. The cosmic bruise. There is a region in the cosmic microwave background that doesn't belong. It was spotted in 2001 using data from the COBE satellite, a roughly circular patch of sky, about 5 times the diameter of the full moon as seen from Earth, where the temperature of the ancient light drops far below what it should. Not a tiny statistical fluctuation. Not noise. A genuine, large, anomalously cold region that the standard model of cosmology struggles to explain. The Eridanus supervoid, a genuinely, observationally confirmed underdense region of space in the same direction, sits along the same line of sight. That void is real, but whether the void alone can explain the cold spot's full depth and size remains contested. In 2007, cosmologist Laura Mersini Houghton at the University of North Carolina said this about the cold spot. It is the unmistakable imprint of another universe beyond the edge of our own. Her model, drawn from the quantum landscape of string theory, proposed that before inflation separated our universe from its neighbors, quantum entanglement between adjacent universes left physical scars, detectable deficits in temperature, detectable voids in our sky. The cold spot, she said, was one. She also predicted a second void in the northern hemisphere of the CMB and connected her model to the dark flow signal Kashlinsky would later measure. Some of her predictions appeared, briefly, to land. But here's the thing. A 2022 analysis of Planck data combined with BICEP and Keck polarization measurements found no evidence for the entanglement signal her model requires. The mechanism she proposed doesn't match the data. The cold spot is still there. The Eridanus supervoid is still there. What caused them is still unresolved. Mersini Houghton's explanation may be wrong, but the scar exists, and the most boring explanation, that it's just a statistical fluke, gets a little harder to accept every time someone measures it, and it's still there, exactly where it was. An anomaly that looks exactly like evidence, and might be nothing. Number 5. The black hole universe. In 2010, a physicist named Nikodem Poplawski at Indiana University published a paper with a very short, very strange sentence at its center. The sentence was, "Our own universe may be the interior of a black hole existing in another universe." That's not a metaphor. That's a falsifiable claim derived from a specific modification of general relativity called Einstein-Cartan theory, which extends Einstein's equations to account for the intrinsic spin of fundamental particles. In standard general relativity, matter collapsing into a black hole hits a singularity, a point of infinite density where the math breaks down. In Poplawski's version, a property of spinning matter called torsion generates a repulsive force at extreme densities. The collapse stops. The matter bounces. And on the other side of the event horizon, a new universe expands. From the outside, from the parent universe, nothing unusual happens. The black hole forms normally. The horizon exists. But inside, on the other side, causally disconnected from the parent universe, a new cosmos is born. With its own space, its own time, its own physics. Our Big Bang, in this model, was a bounce. We are inside. Both National Geographic and Science Magazine listed this among their top 10 discoveries of 2010. And here's the implication that doesn't let go. Every black hole in our universe would be doing the same thing. Every stellar mass black hole, every supermassive black hole at the center of every galaxy, each one potentially a gateway to a universe that will never know we exist. In 2019, the Event Horizon Telescope released the first direct image of a black hole, a glowing orange ring around a dark circle, the shadow of M87's central black hole. At the time, it was described as a triumph of observational astronomy. It might also be a photograph of a universe being born. Looking at that image differently changes something about it. That circle isn't just an absence of light. It may be an absence of here. Number 4. The false vacuum. On July 4th, 2012, scientists at CERN announced the detection of the Higgs boson, the particle that gives other particles their mass, the missing piece of the Standard Model. There were champagne corks. There was applause. Peter Higgs, the 83-year-old physicist who had predicted it nearly 50 years earlier, sat in the auditorium and wept. Then the physicists went home and measured its mass, and they got a number, 125.18 giga-electron volts, and some of them went quiet. Because that mass, when you plug it into the equations governing the Higgs field that permeates all of space, implies something uncomfortable about the universe we live in. The Higgs field has an energy state. Think of it like a ball sitting in a valley. Our universe sits in a particular valley, what appears to be a stable, low-energy configuration. But the measured Higgs mass suggests that our valley might not be the lowest one. There may be a deeper valley, a lower energy state, a true vacuum, and we are sitting in a false one. In quantum mechanics, a field trapped in a false vacuum can tunnel through the energy barrier, separating it from the true vacuum. Spontaneously, randomly, without warning, a bubble of true vacuum would nucleate. Its interior would have different physics, different particle masses, different electromagnetic forces. Chemistry as we know it would not exist inside it, and the bubble wall would expand outward at the speed of light. Stephen Hawking wrote about this. He said the Higgs potential has the worrisome feature that it might become metastable, and that the universe could undergo catastrophic vacuum decay, with a bubble of true vacuum expanding at the speed of light. Here's the part that genuinely deserves your attention. If such a bubble has already formed anywhere within our observable universe's past light cone, we would not exist. The fact that we're here, having this conversation, proves nothing like that has happened locally. It tells us nothing about what's happening right now, beyond the cosmic horizon. The bubble would be completely invisible until it arrived. There is no precursor, no warning. Physics would not send a memo. One moment the laws of nature hold, the next moment they don't, and you never experience the moment in between, because the moment in between doesn't exist. Beyond the observable universe, the laws of physics we rely on may already have been replaced, an expanding sphere of rewritten reality, growing at the speed of light, indistinguishable from nothing, until it's everything. Number 3. The universe before the Big Bang. Roger Penrose is 89 years old, has been working in mathematical physics for over 60 years, and in 2020, he won the Nobel Prize. Not for the theory we're about to talk about, for something else, His work in the 1960s, proving that singularities are a robust prediction of general relativity. Essential, rigorous, foundational work. The sort of thing that earns you a Nobel without controversy. The theory we're about to talk about is controversial. Penrose has spent the last 2 decades promoting something he calls conformal cyclic cosmology. The idea that our universe is one chapter in an infinite book, one aeon among an endless succession of them. At the end of each aeon, the universe expands forever, cools to nothing, until all that remains is a sea of photons and the slow death of the last black holes. Eventually, those black holes evaporate, radiating away their mass as Hawking radiation over timescales of 10 to the power of 106 years. That's a 1 followed by 106 zeros. Beyond comprehension. But then something strange happens in Penrose's model. When all mass is gone, time itself loses meaning, because time, in relativity, is only meaningful to massive particles. And a universe with no mass and no time is, mathematically, conformally equivalent to an infinitely small, infinitely hot, dense new beginning. The end of one aeon becomes the Big Bang of the next. And if this is true, if the universe has been cycling through aeons, then the previous universe should have left marks. Specifically, the supermassive black holes at the end of that previous aeon, in their final billions of years of Hawking evaporation, would have emitted a concentrated wash of radiation. That radiation would survive into our aeon, imprinted on our cosmic microwave background as anomalously hot, circular patches. In 2018, Penrose and colleagues published a paper claiming they had found exactly this. They called the hot spots Hawking points. They said they were the electromagnetic echoes of black holes that died before our universe began. In 2020, another team reanalyzed the data and said the Hawking points were consistent with standard inflationary physics. Not evidence of a previous universe. Just noise. Penrose disputed the analysis. He keeps publishing. Most cosmologists think he's wrong. They say it clearly, in print. And Penrose, a Nobel laureate who spent his career being eventually proven right about things people initially dismissed, keeps looking at the data and seeing something different. He is spending his final years arguing that we can see, faintly in the oldest light in the universe, the dying fires of a cosmos that existed before ours. That beyond our Big Bang is not nothing. That before the beginning is not a meaningless word. That is either a beautiful last act or a cautionary tale about how hard it is to know the difference. Maybe both. Number 2. The Darwinian universe. In 1992, physicist Smolin published a hypothesis that did something almost no theory about the multiverse had ever done. It made specific, falsifiable, testable predictions. The idea is called cosmological natural selection. And it works like this. When a black hole forms, the matter collapsing at its center doesn't hit a singularity and stop. It bounces, generating a new universe on the other side, with physical constants slightly different from the parent universe. Different particle masses, a slightly different strength of gravity, a slightly different speed of light, mutations in the biological sense. Over time, over the vast timescale of cosmic history, universes that produce more black holes produce more offspring universes. Universes that are poorly configured for black hole production become rare. Universes optimized for stars and stellar collapse and the conditions that generate black holes proliferate. Our universe, Smolin argued, is fine-tuned not because of us, not because of the anthropic principle, but because it is the descendant of a long evolutionary lineage of universes that were good at making black holes. We are the product of cosmic natural selection. Life may be a side effect. Susskind, who later developed his own version of the landscape of universes, his own theory of cosmic selection, said about Smolin's idea, I'm not sure why Smolin's idea didn't attract much attention. I actually think it deserved far more than it got. And here's what made it remarkable. It could be wrong. It said specific things about what the laws of physics should look like. It predicted that the maximum mass of a neutron star, the dense remnant of a collapsed star, should be around 1.6 times the mass of the Sun. Any higher, and the neutron star would become a black hole rather than producing one through a different mechanism, which would throw off the selection pressure. The prediction was specific. It was checkable. In 2010, astronomers observed a neutron star with a mass of roughly 2 solar masses. Smolin initially worried the theory was falsified, then revised the parameters. The debate continued. In 2022, a neutron star was discovered, PSR J0952-0607, with a mass of approximately 2.35 solar masses. That's well outside what Smolin's model comfortably allows. The most elegant theory of the multiverse. The only one that behaved like science. The one that predicted things and submitted to being tested. And it may have been killed by a dead star. Leonard Susskind, his theoretical rival, said it deserved more attention than it ever got. He said that. And then, the universe handed back a number that might end it. There is something genuinely tragic about a beautiful idea meeting a falsifying observation. Science is supposed to work that way. It's just harder to watch when the idea is this good. Number 1. The bubble universe. The mainstream answer, the one most professional cosmologists would give if you asked them what lies beyond the observable universe. Sounds at first almost mundane. More universe. A lot more. Probably infinite. Here's what that actually means. In 1980, Alan Guth at MIT proposed cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, a period far shorter than any unit of time we have a name for, the universe expanded exponentially fast. A region smaller than a proton became everything we can see in less than a billionth of a trillionth of a second. Inflation solved several deep problems in cosmology simultaneously. Why is the universe so uniform? Why is it so flat? Why don't we see magnetic monopoles? Inflation answers all of these, but inflation introduced a problem of its own. In 1983, Paul Steinhardt showed that inflation, at least in its most natural form, doesn't stop. It can't stop everywhere at once. Some regions slow down, shed their energy as heat and particles, and become universes like ours. But everywhere else, inflation keeps going. The inflating regions expand faster than the bubbles of normal space can fill them. And so, new bubbles keep forming, forever. An infinite number of pocket universes, each separated from the others by eternally expanding space they can never cross, each with physical constants determined by how their local inflationary field settled. In 1986, André Liondi at Stanford formalized this into what he called eternal chaotic inflation. In his words, instead of a universe with a single law of physics, eternal chaotic inflation predicts a self-reproducing, eternally existing multiverse where all possibilities can be realized. All possibilities. Every combination of physical constants that can be consistent will be somewhere. An infinite number of universes, most of them dark and cold and dead, because their physics didn't allow for stars or atoms as we know them. A smaller subset with stars. A smaller subset still with chemistry. A vanishingly small fraction with something like us. Looking up and wondering, what's out there? Now here is the thing that matters. The thing that changes the shape of the whole conversation. The man who first proved that inflation was eternal. Who showed that it would inevitably produce this infinite sea of bubble universes, was Paul Steinhardt. And Paul Steinhardt spent the next several decades trying to convince everyone that the theory is wrong. Not just incomplete, not just imprecise. Wrong in a deep way. His argument is this: a theory that allows any outcome explains nothing. If inflation can produce universes with any physical constants, then it predicts all of them equally. It can't tell you why our constants are what they are. It can't tell you why we see what we see. A theory that is compatible with every possible observation is not a scientific theory. It's an unfalsifiable story. Steinhardt proposed the ekpyrotic model, colliding membranes in higher dimensions, a cyclic universe that bounces endlessly, as a replacement. He rejected the thing he helped build. He has been trying to demolish his own most famous contribution to physics for over 20 years. Guth and Lind, the other founders, disagree with him. They think the multiverse is real. The debate is ongoing. No resolution is in sight. And here's where this ends up, if you follow it all the way down. The answer to what's beyond the observable universe might be everything. An infinite cascade of bubble universes, inflating forever, most of them unreachable by any signal or probe or thought we could ever send. The answer is real, in the sense that it's a consequence of mathematics we trust, and it is completely, permanently, perhaps forever unknowable, not because we lack the technology, but because the structure of space-time itself makes observation impossible. The boundary of the observable universe may also be the boundary of what science can ever say anything meaningful about. We built a method, experiment, prediction, observation, falsification, and we followed it faithfully, and it led us somewhere that the method cannot follow us. We're not at the edge of our ignorance. We might be at the edge of what knowing can mean. Every theory in this list was built by someone who looked at the same sky you can see on a clear night and refused to accept that the edge of their vision was the edge of everything. That refusal produced all of this: the cold spots, the Hawking points, the dark flow, the false vacuum, the bouncing black holes, the brains, the bubbles. All of it is the result of people pointing at the horizon and saying, "That's not the end." That's just where the map runs out. The map keeps running out, and they keep going anyway. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.